Right. So we are covering some of the textbook number 2. The green colored one will be covered. We did not cover yet dynamics yet, but I may. These are already covered, right? Today we will cover chapter 7. And contents will be history of undersea exploration and manned underwater system and unmanned underwater system. Right. Long ago, right? What happened in Korea in around 1533? Before the in general, or is it before then? Right? 59 to 92. Right. It's in middle of E dynasty. Right. Okay, and then first the modern diving bell. To Koreans, diving bell is famous now. Right? Diving bell. It's a bell shaped. Right? And submarine, diving chamber, and hand-powered submarine. Ideas. And also hand-powered submarine. So many ideas. Still, 1866, there was a torpedo, and U-boat. But U-boat is famous in World War II. Right? So major advances in underwater technology, submarine and underwater communication was through the World War I and II. So bathysphere is very deep operational system. And so around World War II time, right? So for the warfare, scuba equipment is developed. And then just after the nuclear bomb exploded in Japan, right? They tried to use nuclear power first time. This is first time for nuclear engine. Right? This is before the nuclear power plant, right? Because many people don't want to have such a commercial use because of the atomic bomb in Japan. So military can try the first time to use power system or engine, nuclear submarine. So it is another historical moment, also in ocean systems. And then it is comes of submersibles and remote ROV, and then underwater habitats. The apartment or building or city. And then into sheet, like space sheet, but it is for deep water pressure protected diving system, and AUV. ROV and AUV is difference in terms of it is no cables. We'll see later. And then it comes with a glider system. Glider is similar to AUV, but it does not have a big battery inside. And manned system, and then we will go on to unmanned system. Right? And atmospheric is same as here, right? But this is pressurized. Scuba system, diving bell, and then diver propulsion vehicle. It's like one-manned divergence, one-manned submarine something. So water is, you should be contact with the water. This is bigger ones, submarine, submersible, spear, and suit. Suit is very hard covered, like this one. So it is covered, protect from the pressure, and seat is there. This is our lung capacity. Theoretically, the maximum capacity is about 6 liter. Very big, right? Very big, 6 liter. But usually we use only portion of them. Sometimes they use a big breath. But this one is not used. So only used in this range, but regularly in this way. Deep diving for young children, but this is a diving limit for divers. Recreational diving, 30 meters. But you remember that the Seungwoo case, Seungwoo ship, the location was around in this range. So it is possible, but it is hard to operate. So it's an absolute recreational diving limit. But there is a record for scuba diving, compressed air, and saturation diving. In diving hazard, there are 3 main respiration problems. Carbon dioxide excess. This is very similar to when I was young, my home was heated by coal, some special, and then sometimes we have heated by carbon dioxide problems. Sometimes myself too, a little bit. Oxygen shortage is coming together, right? Oxygen shortage. And this is special, right? Oxygen poisoning is also problem because it's a high pressure. Okay. And then this is more popular problems of decompression sickness and inert gas nitrogen narcosis. This is very important for scuba divers, even recreational people. And when you go down deep, I already told you that 10 meter gives you one more atmosphere pressure, right? ATM. So 2 meters. So 30 meter, then it can be 4 ATM, right? 4 ATM. So your body is compressed, right? Compressed. Your blood is also compressed. So if you open a Coca-Cola or other some kind of drinking soda system, you see that bubble is coming out. Because what? Because pressure is down, so that gas in the liquid is coming out. Right? Very similarly, when they make that kind of a soda drink, they compress the bubbles into the water. Right? So pressure is high inside. Same thing is happening when we are going down into the sea. The air is coming into the blood naturally, right? Because of the high pressure. And then if you're going up, the bubble is coming out from the blood, right? Same as your Coca-Cola can, right? So blood in the form of bubbles, right? So you need to coming up slowly, so that body can adjust. Otherwise, there can be a bubble inside your blood coming out, right? Bubble inside bloodstream. That gives you sickness. Right? The other one, nitrogen is something pressurized, because the compressed air, And breathing equipment, there is a regulator, pressure regulated. Depending on the pressure, right? Depending on pressure is changing. So that it should be regulated. Too high is not good, too low is not good, right? So it should be regulated. Semi-closed, then is or closed or open socket means the air coming from the tank to your mouth and then go into the tank again. That can be a closed system, right? Otherwise, it's open system. It goes outside. Right? So this is diving bell. But there are different kind. This one is very good, right? Good. So you can stay inside. But the one we covered in several cases, this is not only just a open-ended bell. So that there is some air inside because of the shape. Air is captured, right? That's all. So they can stay some time inside as a rest area, just a rest area, without helmet or sometimes because you can provide airs from the top through the cable, right? So the rest area without a helmet, right? That is the only provision. But here it is under pressure, so atmospheric pressure can be maintained in this way. Same as a submarine, so it should be big. So depending on the size and equipment, different type of diving bells. Submarines. 장보고 class is called for Korean, very small. Comparing to Soonhung Han is a little bit big, but still in this range. So this is 장보고 2, and we are now developing 장보고 3 is 3,000 ton, but still smaller. And then this is a U.S. Seawolf, Los Angeles, Ohio, sometimes big enough, right? But this is all Russian. Kilo, Sierra, Oscar, Delta, and Typhoon class is biggest one. Right? So Typhoon class, 48,000, right? 48,000. Then it is 3 times more, right? 3 times more. But no, 30 times, right? 30 times, not 3 times. So we are now building 3,000 ton. Even this is 12 times bigger. Because this should be nuclear, and these are all diesel type. I already explained this one before. Yes? No? Can you remember this? Yes? Yes. I did, right? Anyway, for diesel engine submarine, the engine can be used when the air is supplied. The diesel engine needs air, right? So when submerged, you only use battery. That's the limitation. Also, the noise coming from diesel engine is easy to detect by enemy vessel. So they cannot stay long enough inside the water. Only several days. Right? Typical nuclear is they can travel 60,000 nautical miles. 60,000. So, what is the length of the globe? What is that? Around the world, what can be that size? Guess? Number? You found this? Google? No. Probably 20,000 nautical. So it's 3 times more. around the world. So long enough, but that is technically limited. But as a human, you cannot stay. You cannot stay. So I heard that 3 months is a limitation, but the usual operation is 1 month stay for every soldier. You may change, but they want to stay longer inside the water. So probably after 1 month, they change everybody to another troop. Right? That may be the operation. But in say emergency case, you can stay, I don't know, but probably up to 3 months in wartime, right? And non-military submarines. It is for recreation. It is for scientific observation, for deep diversion, right? Deep diving into say 10,000 or 20,000 meters, 20 kilometers, 30 kilometers down into the sea. All right, that is the final slide for me today. Submersibles. So this is small, right? You can see that the size of the human is comparably small, so that several people, 2 to 3 or up to 5, can stay. So that they do not have enough engine or power or air, so they need to have a cable. Usually, they need to have a cable. That is the case. So that with cable you cannot go far away. So it's a limited range of operation. But you need to have a ship together, supporting surface vessel. You can read a Japanese word is Shinkai 6500. Right? Shinkai. That means deep water 6,500 meter down. So up to. There is Japan's research submersible. Question? No question. Then go on to next lecture.
Okay, I will explain about the unmanned underwater systems. And this is the classification of the unmanned systems. And there are 2 types of unmanned system. First one is ROV and second one is an AUV. ROV is remotely operated vehicles and the AUV is autonomous underwater vehicles. And the ROV is usually tethered, which means online with lines, and the AUV are usually not tethered. So these are the propulsion system or drive system. The ROV have some types of free swimming or towed or bottom crawling, and AUV has propeller powered or underwater glider and some others. And there are some hybrid types of unmanned systems. So these are the power source for the vehicles. The first one is surface powered, which means the surface vessel supplies the power to the unmanned vehicles. And second one is vehicle powered, so the vehicle has the battery and the vehicle can move itself. So all of the power producing capacity is stored on the vehicle in form of the battery, fuel cell, or some other means of power storage needed for vehicle propulsion and operation, like research and detecting. And also there can be hybrid system, mixture of the surface and submersible supply power. And for AUV, there is degree of autonomy, and the 4 classification can be made it. The first one is fully autonomous. Second is semi-autonomous and teleoperation and remote control. So actually the first and second one. Second is actually the AUV, and these two will be the ROV. So fully autonomous system is expected to accomplish its mission within a defined scope without human intervention. And semi-autonomous system is that the unmanned system and the human operator conduct a mission and require various level of human-robot interactions. So there is some human-robot interactions. And teleoperation needs the feedback from human. After human detect the human read the sensor feedback, and they give feedback to the vehicles. And remote control is human operator is needed, and without sensor feedback, and directly controls the actuators of the system. In this mode, the system takes no initiative and relies on continuous input from the user. So this is the advance in vehicle autonomy. There is 3 generations of unmanned underwater vehicle technology, and the 3rd generation is like a swarming operation. So multiple vehicles can operate each other, and they can be distributed controlled, and fully automated mission planning. And this is the communication methods, and the hardwire. There will be hardwire communication, or acoustic communication, optical communication, and radio frequency communication. These are the without wires, but it usually restricted with the depth of the vehicles, and there will be some hard part for yes. So there is here is the mission classification for AUV and ROVs, and AUVs are usually made for survey or exploration and monitoring and inspection, and that is the AUV. And the ROV is usually larger one, so it can be install something or construction or repair, and can be used for maintenance. So their difference is the power consumption and operation intensity and intelligence level. The science missions are usually for the AUVs, and the missions will be like oceanographic research and environmental monitoring, and bathymetric survey, which means the depth of the water, and the ocean archaeology. Next is military missions, like intelligence or surveillance and reconnaissance, and anti-submarine warfare. Also, they can do the minefield operation, mine mapping or mine laying or mine sweeping. And next is industrial missions. Usually it will be the ROVs, and industry application areas will be hydrocarbon field development and underwater CO2 storage system, and ocean renewable energy development, and subsea to shore underwater construction. So these are the examples of ROV. Let's see the short video clip. This is underwater inspection by remotely operated vehicle at 153 meter deep, which was the scuba diving record. So they can do things underwater where human cannot be approached. They're checking the connections for oil construction, something. And it can go to 6,500 meters underwater, and its weight is 3.6 tons in the air. And this is another example, and it can go deeper. And this is from Japan. Its system has the vehicle and the launcher in the middle of the sea, and the vehicle can go to 7,000 meters underwater. And this is from Korea, Hemire. This is also can go to 6,000 meters and 3.6 tons. Usually the ROVs are big, like some meters, and can go to some 1,000 meters underwater. And this is the towfish shaped vehicles. This shape called towfish, and it usually used for AUVs. This is the example of AUVs. You can see the diameter and the length is way smaller than the ROVs, and also it is very light, and it cannot go to deeper than ROVs. The maximum operating depth is 100 meters, and it has a battery, so its endurance for research is 6 to 10 hours. So there is another video clip for AUVs.
We've come here to see for ourselves how the Bluefin AUV operates.
AUVs like the Bluefin 21, they're the tools you would use to conduct a wide area dive, clearing a multitude of water.
Will O'Halloran is a marine operations engineer for Bluefin Robotics, which designs and builds these autonomous underwater vehicles in Quincy, Massachusetts.
If this were a mission, real mission, what would be happening?
So the next thing that would happen is the radio instructions would be received that red antenna there. The vehicle would say, okay, I'm going to start this mission. The propeller would turn up and I'm going to dive.
Here in Boston Harbor, the water is only about 40 feet deep, which is easily manageable for the Bluefin because this autonomous vehicle is used to working in depths several miles below the surface.
The Bluefin 21 can dive about 2.5 miles, but Flight 370's wreckage in the Indian Ocean may be deeper than that. It takes about 2 hours for the Bluefin to reach the bottom, where it can operate for another 16 hours. It scans the ocean floor as if it's mowing a lawn, using side-scan sonar, which identifies objects that stand out from the seabed.
When it's working with the side scanner, it's not just taking pictures, right?
No.
It's measuring sound.
Correct. What it's doing is it's actually converting sound to electricity and then turning that electrical value into numerical value. Then you turn it into an image.
When it returns to the surface, scientists download the sonar data to computers. The results may look something like this.
And what we're looking at here, for example, this is a shipwreck in Boston Harbor. So you can see how it's different than the area around it. You can see there's parts of the steam engine right there.
If something catches their eye, the Navy will send down a high-resolution camera on the Bluefin 21.
Then these are the examples for AUVs, and it's from Norway, and it's much bigger, and its endurance is also 1 day, and it's Odyssey 2 from MIT, and it is also for research. And this is Abe, but it can go to deeper operating depths. It has larger operating depths. And this is from Japan, and this is bigger one for AUV, and it's from Korea, and it's smaller one, and cruising distance is just like 10 kilometer. And this is semi AUVs. And this is the glider type AUVs, which has no propulsion system, so it can stay longer underwater. So its range is like 400, 600 kilometer, and this is also gliding underwater, and the endurance is like 30 days with electric sensing, or 3 to 5 years for thermal sensing. And this is the end of my presentation. Thank you.
Good evening. I'm Dongchan Park. Today I will going to lead the discussion. I prepared 2 subjects for today's discussion, and the first one is about the underwater tunnel. As the first underwater tunnel in the world, the tunnel between England and France in 1994. With this start, many underwater tunnels were built, including tunnels in Tongyang in Korea, and also in last year, SK Corporation made the Euro-Asia tunnel between Europe and Asia. So there has been some debates whether building under-ocean tunnel between Korea and China or Korea and Japan, but these are postponed. So here's my question. How do you think building underwater tunnel in nation or abroad? So let's here right 3 are on agree, and left 3 are in disagree. So let's talk about this. Sorry.
I have just one question. Is it possible to see through the water in tunnel? Impossible or possible? I don't know why.
Usually not.
Then why should we build the underwater tunnel? We can build a bridge. Is it cheaper than build a bridge?
I didn't check it, but when there was a agenda for building underwater tunnel between Mokpo and Jeju, there was some advantage, a kind of advantage for building the longest train, rail, or KTX in the world. So, I
Only the problem can be depth of the water. If you want to make a bridge, sometimes you need to have a floating type. Otherwise, depth is too big.
I think it really depends on where, and if it is deemed economically feasible to build a tunnel, I think a tunnel has more advantages than a bridge, because a bridge would, for instance, disrupt shipping traffic, and on top of my head, that's the only advantage. I don't know about the price, but I could imagine that maybe building a tunnel is slightly more expensive than building a bridge, but it really depends on the location. And you mentioned a tunnel going from Korea to China. By Korea, I'm sure you mean South Korea, and the distance from South Korea to China is quite large, like a lot larger than the distance between, or the length of the Channel Tunnel between France and England.
No.
So I think that may be pushing it. It might be more economic to just take a plane. But yeah, so it depends on the circumstances. But if under the right circumstances, absolutely. I think it's better than a bridge.
Thank you. Any other opinion? And then let's talk about the next next thing. The use of sonar. Sonar stands for the sound navigation and ranging. It is for detecting submarines and first developed in the First World War. The reason why they use sonar is that, as you know, waves are observed to the water, and just use sonar, just use ultrasonic waves for detecting something, but it is very harmful for whales who use ultrasonic wave for communicating. So we can see annually poor whales killed by human indirectly. So many NGO and corporations like Greenpeace are opposing this tech. Yeah, here is my question. It is very useful for human, but very harmful for whales. So how do you think of the use of sonar?
Do you mean that sonar is not good for animals?
Yeah.
I think it's a bit moral problem, not about the technical things. But if we can find some frequency that doesn't affect some the whales, or we can still transfer the signal, then maybe they would be the best. But actually, we made this sonar a big long time ago, but it's not still. We didn't still found those frequencies, so I think it's not that possible. But if we can, it would be good.
And it is inevitable thing. Thank you.
I think that the extinction of some species is not related about the sonar, but related about the environmental pollution. Sonar could be a little bit harmful for whales, but the majority of the harmful things coming from the environmental pollution. So I think, and definitely we should use the sonar, because there is not available technique to replace the sonar?
Oh, yeah.
I think that, for instance, in submarines, you can use sonar to communicate with other submarines or the land, because you cannot use radio signals. As I found out when I was doing the homework. But you can also, instead of using sonar, you can use something called ultra low frequency, something. And if you use that, you can only transmit a few bits every minute. I think it was like, depending on the frequency, you could transmit like 120 bits per minute. So it's very limited, but maybe if you can avoid using sonar, then avoid it. But if not, then maybe you have to use sonar.
So everybody is supporting now. No against.
Any other opinion? Okay, then let me conclude. We are going to use sonar. So, yeah, thank you for listening.
How about the conclusion for tunnel?
Tunnel. It was some complicated problem, I guess, related to social problem, politics. Any comment for Professor?
No. You are saying it's not technical or economical problem. It's more political problem. Alright. Hey, thank you. What is the schedule then? Next is Tuesday night. No, next week we have a classes, yeah? Let's see. Next week, 23, only one class. 23 is what day is it? Tuesday? Morning? Yeah. Right. Only one class. Alright, see you on Tuesday morning.
One more.